Welcome you all to the Spark Research YouTube channel. This is Dr. Vichan, Assistant Professor in the Department of ECE. And in this session, we are going to take some previous year question paper for this particular course, Analog and Digital Communication. So let's see some examples here. So first of all, the question belongs to the first year. Let me talk about it. So the total marks is of 75. First of all, this is very general pattern, right? Out of 75 marks, it will be divided into the three parts. So part first, that is MCQ based, and the MCQ, how many MCQ? Total 20 MCQ, right? So one example of the MCQ we can see here, that is a product modulator produces a dash type of the signal, right? And part B, that will contain the 5 question, and each question will carry the how many marks? 8 marks. So total it will be 40 marks, right? And part C, that will contain only one question, and one question will be of 15 marks. So total 20 plus 40 and plus 15. So total it will be 75, and that 75 will be converted into the 40, right? Already 60 marks has completed for the internal, right? Okay, so let's take the questions. We will take the primarily the questions from the the long questions, the short question and long question both. So here 5 questions will come from 5 different units, right? So from first units, what will be the question? So from first unit, question is with neat circuit diagram, explain the operation of collector modulator. So this is the one question. Either you can solve this with the relevant circuit diagram and equation. So how a Foster-Seeley discriminator extract the modulating signal. So this is demodulator question, and this is the modulator question. So first one, modulator or demodulator. So you can solve any one of them, right? So I'm going to talk the solutions also in the very short. So here is that like circuit diagram how modulated signal can be produced. So here you can see here your signal is there, and your class C type of amplifier we are going to use here, and RF amplifier is here, and with the help of that you are going to receive the output signal, right? So class C amplifier is biased at cutoff, conducting only for the brief carrier pulses, right? And what is the principle of operation? So class C amplifier is biased at cutoff, conducting only for the brief carrier pulses, and then modulation transformer, that is T1 here, this one, and adds or subtract the amplified MT, the fixed DC, right? And so VC, that is your carrier, and plus the message signal, so it will add or subtract, it depends on that, right? So finally here you, what will be the output is your modulated message. Here is your message signal, suppose the, and carrier signal, message signal and the carrier signal, and then you will get the modulated signal. So this is amplitude modulated type of the signals, right? So modulator one. Now we'll take the demodulator. So demodulator means we are going to talk about that. This demodulator is for we are going to take the for narrow band, and actually this will be valid for amplitude modulation also. So Foster-Seeley method we are going to use. So how will it work? Foster-Seeley method. So primary tank consists of L1 C1 and L1, and the secondary C2 L2. So here you can see here C1 L1 both are there, and C2 L2 both are there here, right? And L3 is common, right? So in between that L3 is there, and here the phase shifter, this capacitor will shift the phase, and then it will pass here, right? And either it will pass in this loop or in this loop. So here choke L3 is the DC return path for diode D1 and D2 both, right? So either it will pass this one and this one, both return path for both. And register R3, R4 are the lead register, and the bypass C3 and C4 will remove the RF. Okay, So and capacitor, this will use to shift the phase by the 90-degree. So carrier moves up to one side of the center and the balance condition is destroyed, and one diode conducts more than the other. This results in the voltage across one of the resistor being larger than the other, and the resulting voltage at the output. So from unit second, what will be the question from here 22? So super heterodyne receiver, right? And they are asking about the AM type of super heterodyne receiver. And the second question, that is either question is that derive the general expression of figure of merit of FM, frequency modulation figure of merit, right? So figure of merit is nothing, the power in the, the uh, energy in the sideband divided by the energy or the power in the carrier, the overall, right? So here that one we have to find. So first let's see here power. So Fm, that is figure of merit, that is power in the sideband divided by the power in the carrier. So we are going to find out the power in both the powers, and then you can take the ratio. So power of carrier, you can see here, that is nothing, amplitude square by 2, and the power of the massive signals, this is the expression for your frequency modulation. So you can check it here that frequency is varying, so omega t plus kf and integration of minus infinity to 2 mt dt, right? And then here beta, you can find this is the modulation index, that is this is important one, right? Beta is equal to kfm divided by omega m, and then put the values and you will get the figure of merit, that will be 1.5 of beta square. Okay, so super heterodyne receiver, this from the same questions you can see here, like we have already discussed about the super heterodyne receiver in our previous session, so you can go through the content which we have discussed in the unit 2, right, for more details. So super heterodyne, your IF frequency is important, so that is your 10 kilohertz. Just and I frequency, how will you find? This is RF minus FLO. So here you are going to detect the your masses, and then I know, so then you can start the demodulator based on the local oscillator. This will pass the frequency, and then finally you have the addition here, right? And after that, you can detect and amplify the masses. So these are the techniques from question from unit third. Now, what is the question? Question is the PCM, right? PCM, pulse code modulation, and either or question is that interference, right? So what is the interference? Crosstalk, how does it crosstalk, and give a quality analysis based on the interference gained I pattern also. So first let me see the I pattern, right? The second question we will talk the ISI and crosstalk. So in digital communication, ISI is a form of the distortion where one pulse or symbol is spread out and interface with the adjacent symbol in the same signal. This makes it difficult to resolve the distinguish between the 1 and 0. Right. So this is the ideal case. See here, this is the very ideal one. This is 0. This is 1. Like this is very ideal case. But what will happen actually? Actually, you are going to receive this type of the message. Say, the 1, and then here 0. So here, like in this region, what is happening? Whether signal belongs to 1 or 0, in this region also where signal belongs to 1 and 0, lots of confusion, right? So that is why this inter-symbol interference will occur. Okay, so now this region and both the regions, if we'll plot here now for multiple signals, then it will they create a some I type of the pattern, right? So this is the 1 and this is the 0. For 1 and 0 both we are plotting in the same diagram, then it will the become a I pattern. So now this is the cutoff limit. If it is greater than this, you can say this signal is 1. Less than that, then you can say the signal is 0, right? So you can identify jitter, that is width of the crossing, then the zero crossing distortion and the slope of the eye, all these things, right? So it is very clearly that if eye is closing higher like this, it means that signal have the very less noise, and if eye is like that, the closed eye means like this, of course the signal have much more high noise, right? So and the PCM system here, pulse code modulation, this is the one type of the digital modulation that we are going to discuss here. So first of all, what is this PCM? So sample on the x-axis and the quantize on the y-axis. So then it will convert it into the PCM, that is digital signals, or you can say that this is the simplest technique. So this is called the pulse code modulation. So this is the sampling on the y-axis, and of course this is the sampling on the x-axis. So sampling on the y-axis means that is called the quantization actually, and then this is the PCM technique. And like this gap, right, this is the gap here, that is this gap may be the non-uniform or maybe the uniform. So if it is uniform, that is the very simple case, and for non-uniform case, like you can vary this gap depending, it depends on the like the values of the variation in the amplitude. So if you are changing the amplitude the gap, that is this is also called the gap, that is the quantization level, you can also call it as a quantization level. So if you are varying it, that is called the compounding. So there are the two law, that is a law, mu law. So based on that you can vary. So here is the equation, that is how your step size, this is also called the step size, that is how the step size can vary. So y is equal to 1 over ln 1 plus mu. So this is mu law. So that is how it will vary, and value of the mu you can check it, right? Similarly a law. So these are called the compounding technique. Okay,
right?
so
Similarly,
here
for
we are.
PSK, differentially PSK, you can check here. For coherent, the probability of failure is less, non-coherent it is higher, and probability of failure you can find, this one equation is here, right?
So this is 24, that is fourth number question. Briefly explain the generation and detection of the DPSK signals, and this is QPSK signals. So here is the DPSK, and here is the QPSK. So for QPSK already we have discussed. For more details you can go to the slides that we have discussed in the fourth unit. So here is the QPSK generations, your binary to the multiplier and the output, and here is the received signal, and then the filter, sample, decision rule, and then finally your digital output. Okay, so final unit, from the final unit, the question is from the Shannon-Hartley capacity theorem, and then also you have to find out the one numerical, that is you have to find the reduce the channel capacity, other things are given, and this is one source coding. You have to find the source coding encoding technique and the efficiency, right? Shannon coding. So what is the Shannon-Hartley capacity theorem? This is very important formula. You should remember C is equal to B log to 1 plus SNR, right? B is what? Bandwidth, and SNR is the signal to noise ratio. So very important equation. And the capacity limit is this. You can neglect the one, you will get the capacity limits. Also you can convert it into the dB scale from SNR, and you will get the 63 if you put. Okay, from this numerical you can put the values of SNR and the bandwidth, and then you will get the C value, right? So here the bandwidth is given 3.4 kilohertz, and SNR is also given 18, that you can convert into the the scale in the dB scale, and from dB to the power values, that's SNR, and then put it, and you will get the C, and finally answer will be 20.4 kbps. Okay, here is a question related to the how to the do the sun encoding. So we have already discussed very briefly in the unit 5th, so you can go through that. Here I have taken the same content that we have discussed, and you can replace these probability values, and with the help of the same technique you can solve. So what is the technique? So technique is that just divide your first of all arrange the probability in descending order, and divide into the two team, team 1 and team 2. And condition, what is the condition to divide the probability? So the addition of the both team have the almost equal probability. So that is the condition. And keep on dividing, you will get the patterns of the code. After getting the patterns of code, find the entropy using this, the equation, and the p of x, and then log of 1 over p of x, and then the code, the length, average code word length, that you can find it using this code that you have us find that using the Shannon code, and then take the ratio to find the efficiency. That's all the the short questions. Now here we will take the long question. So 26 is very long question here. So see the question. So here the expression for the binary PEM asking, and then maximum SNR for optimum filter, and then corresponding impulse filter and the probability of error they are finding. They are asking, right? So here is the the h of t, that is your expression for the PM signals, the maximum SNR that you can find. Binary PM, actually this is your binary PEM signal. Here RT is the actually signal plus noise both, and SNR is you can find out. And impulse response you can find, this is the impulse response for this matched filter, right? And so SNR also you can find. The same things you can rewrite like this. Okay, PAM signals you can details you can see here, that is the PM signal. What is this PM signal? Also you can go refer to the content that we have discussed in the third unit. Another question, last question, this is array digital the modulation with relevant equations. So array digital modulation technique they are asking. 8 array PSK and 16 array QM and binary FSK, like that. Okay, so here is the signal space diagram. Again we have already discussed, so again refer to the which unit. This belongs to the QPSK fourth unit, right? So first of all, write down the equation for your message signal, that is SIT. This is very general one, and put the value of I in order to write the different signals. So since here we are talking about the 8 array, right? So we'll have the total AM is equal to 8. So distance will be this minimum distance in QPSK, and you can also find the right. So for QAM, also QAM, that is quadrature amplitude modulation. Here we are going to vary the both phase and the amplitude here. So distance again you have to find out, and then the masses you can find, right? So phase we are changing. After finding the masses, you can have the constellation for the different signals that we are going to use for 16, like there will be the 16 masses. Okay, similarly here binary FSK, like here different frequency will be there, right? And the signal space diagram also you can draw. Okay, so thank you to join the session. If you have any doubts, please drop a comment.